We have our exam, and then that's it. We will be done for the rest of the week. And then Monday we'll pick back up. We'll start in chapter 4, and then we'll continue on. So next term we actually do, I think we do 4, 5, and 7 for the chapters, I think. I'll have to look again. Yes, Mason.
How much is, like, percent, or what percent is this?
So this is the same as your tests. Okay, so it's all in a 50% category. Okay. Ben. We've been reviewing for the last several days. Nope. This is. Okay, so tomorrow when we meet, we'll meet right here at the same time, 12:07, and then 12:07 to 1 is considered the retest time. And so if you want to retest chapter 1 or chapter 2 again, you can do it again. Even if you retested chapter 1 twice already, you can do it a third time. All right, now average those grades again. Okay, you can only do either 1 or 2, so that would be during this time. Okay, if you choose not to retest, that's fine, but I want you to remain quiet for those that do want to retest. And then at 1:05 will be officially the time for our exam. Will be all multiple choice. Okay, and potentially going to have you do it on Schoology. We'll see. I might have you upload it to Schoology, and then that way, as soon as you hit submit on Schoology, it'll tell you what you scored on it. Okay, and it's multiple choice, so there's no partial credit. Either you got the problem right or you got the problem wrong. All right, and then I will input that into the grade book, and then we will be done. We won't meet, obviously, the rest of the week until the following Monday. Back at it, and we'll pick back up. All right, any questions? All right, so today, radical expression. So just a quick review of radical notation. Simplifying radicals, like if I have square root of 27, that can be simplified. All right, operations with radicals, and then rationalizing the denominator. So if you have a fraction, you never want to have a denominator with a radical in it. All right, so let's do a quick warm-up. First off, cube root of 64 using exponents. How can I write the cube root of 64 with exponents? So this would have been from Friday. How can I write that? Dayton. 1/3. Okay. So this is saying what cubed will be 64? Any guesses, or anyone know what that is? 4. Okay, so 4 cubed is 64, so the cube root of 64 is 4. Okay, write 27 raised to the 2/3 in radical form. So what's going to go up here in my index position, that top left, will be a 3, and then this becomes 27 squared. All right, so this was kind of a review from Friday, working with rational exponents, rewriting as radicals, or vice versa. Okay, so now radical expressions. So this is exactly what we just did, but this is in variable form. If I have a raised to the m divided by n, that's the same thing as n, the nth root of a to the m power. And how I always remember these, I always remember them as squareds. Like if I think of square root of x, well, that's the same as x to the 1/2. So how I always remember this, I always think of it as square root. Okay, square root I know is to the 1/2 power, and then that helps me make that connection rather than trying to just memorize a to the m over n, the nth root of a to the m. Rather than trying to do that, I just think of square root every single time, and then I know what that one is, and I don't mess this up. Okay. Let's practice a little bit. Write each root using exponents and evaluate. So what would be my exponent on negative 32? Dean, what do you say? 1/5. Okay. Is this possible? Can you do an odd root to a negative number? We know with even roots, we bring in that I. Can we do an odd root? Yep. Any guesses on what we can raise to the 5th power that'll get us negative 32? -2. So -2 is going to be the 5th root of negative 32. This one, we could really write this as 16 raised to the 1/4 power. But this one, we are only working with real numbers, so we are going to say this one is undefined. Okay, we're not working with any imaginary numbers on this. So an even root of of a negative number, we're undefined. We're only working with real numbers right now. Okay, this big one. The 6th root of 64 divided by 729. So let's transform from the 6th root. What would this be for the exponent of this piece? Ben, what do you say? 1/6. Okay. Question, is this the same as 64 to the 1/6 divided by 729 to the 1/6? Can I do that? Yes, those are equal. 64 to the 1/6 power, you can put that in your calculator, you get 2. 729 to the 1/6 power ends up being 3. So this mess raised to the 1/6 power actually makes it a little bit easier. Simplifies to just be 2/3. Okay. Now let's write from a rational exponent, or I'm sorry, yeah, rational exponent with a fraction into radical form and simplify. Question for you, could I write this as -1 times 16 to the 3/4? Could I rewrite it like that? Yep, I can write it like that. So now really I have -1. How can I write 16 to the 3/4 with a radical? What's going to go in that top left, that index position? The 4. So this would be the 4th root of 16 cubed times -1. 4th root of 16 cubed ends up being 8, and so this would be a -8. All right, so we can use this negative. This one is not necessarily undefined because we could break it up and we could say, well, really, this is -1 times 16 to the 3/4. If it's already under a radical, you can't break it up and bring out an I. We're not working with this. But when we're in this form, we can write it and bring out that -1, so we don't have to worry about a negative under the radical. All right, 3x raised to the 2/3 power. Is this the same as 3 to the 2/3 times x to the 2/3? No. Okay, if they had parentheses around 3x and it was raised to the 2/3, yes, this would be true. But we are not applying that 2/3 to the 3. It's only on the x. So really I have 3 times x raised to the 2/3. So this will be the cube root of x squared. And this is as far as we can go with this. of this one, 3a plus b raised to the 1/4 power. Can I write that as the fourth root of 3a plus b? I'll even put this in parentheses and say this is to the first power. Is that equivalent? Yeah, can do that. Okay. So again, do not make the mistake of thinking that this 1/4 applies to both terms. Not true. Okay, it's 3a plus b raised to the 1/4 power. Think of it as 3a plus b squared. We'd write 3a plus b times 3a plus b. Okay, it's that whole thing that's being squared. Well, this is that whole thing raised to the 1/4 power. So yeah, we can write it as a radical as a fourth root of that quantity of 3a plus b. You don't have to put in parentheses raised to the first power, but I want to do it just to clarify what exactly is going on. All right, some rules for radicals. And this is going to get us into simplifying with radicals. First one is the product rule. If I have two radicals being multiplied and they have the same index, that n is the same on both of them. It only works if that n is the same. I can rewrite this as the nth root of a times b. We've done it going in the reverse direction. If we have the nth root of a product, we can break it up. So say we had the square root of 27, we could break that up and say, well, that's the same thing as the square root as 9 times 3. Square root of 9 times the square root of 3. So these go both directions. Quotient rule. So this would be the nth root of a divided by the nth root of b. We can break up any quotient because sometimes it might end up being where, say it was the square root of 4/3, well, we'd say that's a square root of 4 divided by square root of 3, which is actually 2 square root of 3. So if it's a square root that you can do it. But if it was like, say, square root of 5 over square root of 3, we'd leave it as square root of 5 over square root of 3. So again, these go both directions. If you have a fraction with the same index of a radical on top and bottom, you can rewrite it as 1. And then next one is the power rule. Okay, so I'm going to put parentheses around this just for clarification. So I went the mth root of the nth root of a. But I put around parentheses, think of it as just one piece. So the nth root of a is going to be raised to the 1 over m. All right, so we've done those power rules. We can bring the index. And so I'm taking that whole piece, my radicand, which is under the radical symbol, raising it to the 1 over m. Now, what's in my parentheses here, the nth root of a, I can really write that as a to the 1 over n. I still have this 1 over m going on the outside. I multiply when I cross my parentheses, so this is 1 over n times m in the denominator of my rational exponent. And then I could take this rational exponent, I could put it back as a radical with nm in the index position all over a. So all of those steps are equivalent. So if you're taking the radical of a radical, you can essentially just combine the indexes with multiplication and then have it under your radicand. Again, this goes both directions. Okay, if you have some product going on here, if you had say 3x, you could think that is the cube root of the x root of a. All right, so let's do some practice with some simplifying. So if I'm multiplying two radicals that have the same index, that says that my index will stay the same, but it'll be m times m squared. And so that's just the cube root of m cubed. If I were working with a quotient, well, we just talked about this. This is the fourth root of a divided by the fourth root of b to the fourth. My numerator is still fourth root of a. What's the fourth root of b to the fourth? Be just b, okay? Because if we want to write this with a rational exponent, that's 4 over 4. So it's b raised to the 4 over 4. So the fourth root of a all over b. Okay. Would a be what? Ah, yeah. So Tay's asking about this one. The cube root of m cubed. Yeah, let's take that a step further and let's just call that m. Good. Tay gets an extra point on the exam tomorrow. Okay. This one, the fourth root of the square root of 3. What's going to be in my index position up here in the top left? I'm working this one all the way out to the end. What's going to be in that index position? Simon, what do you think? Nope. 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 Let's go all the way to the answer. Be 8. Okay? Because really, this is going to be from, yep, okay. So this one is really the fourth root of square root of 3. So let's just write this as 3 to the 1/2. Right, like that. Okay, square root of 3 is really 3 to the 1/2. So this is 3 to the 1/2 raised to the 1/4 power. We would multiply across, so this becomes 3 to the 1/8 power. Rewritten with a radical, then this would be the 8th root of 3 to the 1st power. And this gets back to the previous slide when we talked about that power rule. Okay, if we have the mth root of the nth root, we work it all out, it's actually just multiplying those two together. So this was the fourth root and the square root. So the 4 times 2 gets us the 8th root of 3. All right, let's do some simplifying of radicals with just numbers. So again, we're looking for perfect square factors. Okay, let's start listing out perfect squares. What's the first perfect square? 1. What's the next one? So 1 is a perfect square. Is 2 a perfect square? 3, 4, 5. What's the next one? 9, then what? Then what? Okay? So again, this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and we could keep going on. So when we simplify with numerical radicals, we're trying to check to see if there's a factor that is a perfect square that I can break this up to be. So 175, can I divide that by a perfect square? Or what's the largest perfect square I could divide that by? Maddie, what do you think? 25? 25 times what is 175? 7. Okay? So my radical properties say that I can break this up, and I can say, well, square root of 25 times 7 is the same as square root of 175. What I can also do is I can rewrite this as 2 separate radicals. So square root of 25 times square root of 7. The reason I do that is because now I can do square root of 25. Square root of 7 stays. So square root of 175 simplified is 5 root 7. Okay. What about this one? So this is really -3 times the 5th root of 32. So I'm not going to worry about that -3 yet. So really what I'm trying to find here are perfect fifths. Okay, let's start listing this out. What would be 1 raised to the 5th power? 1. What is 2 raised to the 5th power? So it's 2 times 2 times 2 times 2 times 2. Got it, Ben? What? Ah, okay. So 32 is a perfect 5th root. And so really this is -3 times, what's the 5th root of 32? 2. Okay, we just did that. Okay, because this was 1 to the 5th and this is 2 to the 5th. So really this simplifies to be a -6. So -3 times the 5th root of 32 is -6. All right, now let's talk about operations with radicals, meaning addition, subtraction, multiplication, division. So first off, let's just review again. The index is that top left. The radicand is what's underneath the radical. And then this 5 in this case would be considered the coefficient of this radical. So it's 5 times this radical. Radicals with the same radicand and the same index are considered like radicals. So like if I had 5x plus 2x, I can combine that to be 7x. Well, if I have the cube root of 7, well, let's say if I have 5 cube root of 7 plus 8 cube root of 7, I can combine that to be 13 cube roots of 7. So we can combine like radicals, but to be a like radical, it has to be the same index and the same radicand. And there might be some manipulation to get those to be the same. Okay, so like this one. 3 times the 4th root of 11pq minus 7 times the 4th root of 11pq. I could simplify that to be a -4 times the 4th root of 11pq. All right, we can add and subtract like radicals just like we did combining like terms. All right, but it has to be the same. 5x squared and 5x cubed are not the same. The cube root of 7 is not the same as the square root of 7. They have to have the same index and the same radicand. All right, so these ones can get a little more involved. So if I asked you to combine with addition, 9x 98x cubed y plus 3x times the square root of 32xy. Well, we're off to a good start because they're both square roots. So we have our index the same. Our radican are close, x cubed. We have x and y essentially on both of them. All right, let's look to simplify this first one. So 98x cubed y. So we're working with square roots. So a largest perfect square factor of 98. What could be a largest perfect square factor of 98? Could do 7 squared, which is 49, because 49 times 2 would get me my 98. So I'm going to break that out. And then I'm going to write this as x times x squared times y. I'm going to separate those on purpose. The reason I'm separating those is because now I can do this all as 1. So my properties of square roots, whatever I have under here, I can rewrite it individually as square roots of each term. Well, square root of 49, that's 7. Square root of 2, that's a nasty number. I'm just going to leave it as square root of 2. Square root of x, I can't do anything with that. Square root of x squared is just x. And then square root of y, I can't do anything with that. So I'm going to, just for organization, I'm going to put this all back together under the radical. So 7x, essentially, I've factored out from underneath my radical symbol. Now, on the right here, I have 3x, and then the square root of 32xy. 32, can I write that as a product with one factor being a perfect square? Well, I could do that as square root of 16 times 2, and then I'm going to just break this up, x times y, and square root, square root of x, and I'll just do square root of y. So this becomes 3x. Square root of 16, I know is going to be 4, not 8. 4 times square root of 2 times x times y. So this becomes 12x times the square root of 2xy. Ah, but that's handy. I have 2xy here, and I have 2xy. Now I do have the same radicand. So 7x and 12x I can combine. So 7x plus 12x is 19x, square roots of 2xy. Like I said, these ones get a little involved, but take it step by step. Break it down, build it back up, get it to be the same. If this had been square root of 2x cubed y, well, no, let's say like 2x to the 10th y or something. If there was nothing further that you can do, then you're done. Okay? But if you have any exponent going on under your radical, see if you can, even if it's an odd exponent, you can always take out the evens and leave it with just an odd left. Let's do another one. Let's do it with some multiplication. So we would FOIL this like everything else. So I'd have root 2 times root 8 minus 5 root 2 plus 3 root 8 minus 15. Square root of 2 times square root of 8, I could rewrite that as square root of 16, which is nice because that's just 4, minus 5 root 2. Can I break up 8 with one factor being a perfect square? I could do 4 and 2. And so this is really 3 times 2 times square root of 2 minus 15, 4 minus 5 root 2. So I have 4 minus 5 root 2 plus 6 root 2 minus 15. I could combine the 4 and the negative 15 to end up being a negative 11. Negative 5 plus 6 would be just a positive 1 or just positive root 2. But you cannot combine like radicals or like terms until you get those to be the same. If it's dealing with square roots, we got some simplification that we can do. Two more slides. This one and one more. Rationalizing denominators. If I want to rationalize 4 over square root of 3, what can I multiply by? Rationalizing means I want to eliminate the radical in the denominator. Kyle, what would I multiply by? What would I multiply by? 4 over root 3. I want to get rid of that radical in the denominator. What can I multiply by? Exactly. So root 3 over root 3. That's really just 1. So I'm taking my fraction multiplied by 1. It's not changing the value, but it's letting me rewrite it without a radical in the denominator. So I have 4 root 3 square root of 3 times square root of 3. Well, that's square root of 3 squared. That ends up just being 3. So rationalize the denominator. We are going to multiply by the value of that denominator. It's not the complex conjugate stuff. It's nothing with that. Let's look at the second one. So this is really 4 root 3 all over 4 root 5. Okay, so when we work with this one, we can start to break it up a little bit. Well, I want to multiply, oops, not equals. I want to multiply and eliminate that radical in my denominator. So I'm going to multiply by the 4th root of 5 cubed, and you'll see why I chose 5 cubed here in a second. So when I do this, I have the 4th root of 3 times the 4th root of 5 cubed all over the 4th root of 5 to the 4th. Okay? We did this one as the square root, so that way when we raise it to the second power, it works. If I had just done this as the 4th root of 5, then it wouldn't work. But now when I have the 4th root of 5 to the 4th, that's when I end up with a denominator of just 5. Okay? Because if I had just done it to 5, it would have been the 4th root of 5 squared. Okay, that doesn't help me out. But when I did it to 5 cubed, It allowed me to combine those exponents with multiplication. I can combine the exponents. That's when I get just that fifth, or the 5 on the bottom. This becomes a fourth root of 375, and then there's nothing I can do with that. So 3 times 5 cubed is 375. That's nothing that I can take the fourth root of. I can't break that up any further. I'm just going to leave it just like that. Okay? But this strategy, so don't instinctively think, okay, all I have to do is multiply by the denominator. You got to think ahead a little bit. Okay? I want these to eliminate each other. And so really, maybe I should put 2 in there to clarify a little more. That would have been the square root of 3 squared. Well, now I need the fourth root of 5 to the fourth. I need those to match up to actually eliminate the radical. Last one. Rationalizing a binomial denominator. If we have a binomial in the denominator, this is where we want to bring in that complex conjugate, because remember, multiplying by complex conjugates leaves us with just a number. Or this is just conjugates. This isn't complex. Complex would involve I. This is just multiplying by the conjugate. All right, so we end up with 1 plus root 2 on top. In the bottom, we would have 1 times 1, which is 1, plus root 2 minus root 2 minus square root of 2 squared, which would just be 2. Those go away. So all I have is 1 plus square root of 2 all over 1 minus 2, which is really 1 plus square root of 2 all over negative 1. Divided by negative 1 really is just telling me that that thing is negative. So I could just bring a negative out front, and I wouldn't have to write it over 1. But it's a negative of that whole thing. Don't just write negative 1 plus root 2. It's a negative of the whole thing. Just like a fraction, 5 over 1, you just write as 5. 5 divided by negative 1, you just write as negative 5. Okay, so negative of 1 minus root 2 is how I'd like to see the final answer on that one. That's it.